here we have a cuboid and the lengths have been labelled on it. So 6 centimeters long, 3 centimeters high, 2 centimeters deep. So this is the same shape as a shoebox. And the question we've got for this cuboid is to find out what is the distance between one corner, so I've labelled here in red, to the other corner on the opposite side, also labelled in red. You can see that that goes through the centre of the cuboid here. So to make it a bit easier to visualise, if we open it up, you can see the labels here for the corner A to the corner F. The question is, what is this distance through the cuboid here? And if we draw a straight line from A to F, what we end up with is a right-angled triangle. So if it fits properly, hopefully that's clear. You can see that from the corner A to the corner F, we have a straight line which makes up part of a right-angled triangle if we draw that shape. Right, so again, if we close the box, you can see that it's completely contained inside. And that's what we've made here. And so the reason that you know that it's a right-angled triangle is much the same way as with a door staying a rectangle whenever you open and close it. So even if we rotate this triangle in the corner, the angle at the corner is still going to stay 90 degrees. So we know the height of this right-angled triangle because we know the height of the cuboid that it's inside, because it's going from the corner F to the corner C. And so if we take this out, you can see that that is the right-angled triangle that we're looking for. So the question is, what is the length A to F here? And if we're thinking about Pythagoras' theorem written on the green triangle here, we need to know the length of at least 2 of the sides to find out the length of the third. So we don't know A to F and we don't know A to C, but if we triangle back into the cuboid, you can see that we can figure out the bottom side there, A to C. Make it a bit clearer if I put in this orange right-angled triangle. So this orange one is flat on the bottom of the cuboid here, and it fits in snugly with the red right-angled triangle, and it is made up of the corners A, B and C. And we know the length AB because that's the length of the box, so 6 centimeters, and we know length B to C because that's the depth of the box, so that's 2 centimeters, and they share this length A to C, which we don't know yet. That's what we're going to use Pythagoras' theorem to figure out. And so even though they're not in the same plane, they share that length with each other. And if I take them out and lay them flat, maybe that will also become apparent. So if you had it lined up, you can see that they're the same length to each other. So first off, what we do is we find out for the triangle ABC, what is this length AC? So if we're using Pythagoras' theorem, we know that the 2 short sides squared, so 2 squared plus 6 squared are going to equal the hypotenuse of that long side, so in this case AC squared. And if we do the calculation for that, so 2 squared is 4, 6 squared is 36, still going AC squared. Add these together, we get 40 is equal to AC squared. So therefore AC squared, therefore AC is equal to the square root of 40. Now if you put this into your calculator, it's not going to give you a rational number. So it's a number which goes on forever and doesn't repeat. So it's good to keep it as the square root of 40 whenever you're doing the calculations. So you see if I type that into my calculator, it gives me this 6.32 and so on, but it doesn't repeat. And if I just put it in, then it simplifies it into what's called a surd. But if you don't know that, don't worry. So back to the problem here. So we now know AC is equal to the square root of 40. So we have this bottom side of the right angle triangle that we're interested in. So we know then that for this one, we have 3 squared plus the square root of 40 squared equaling AF squared. Remember, AF is this length through the box that we want to find out. And so if we calculate these ones together, 3 squared is equal to 9. The square root of something squared, those operations cancel each other out, so we're just left with the 40 here, equaling AF squared. So 40 plus 9 makes 49 for AF squared, and therefore AF is equal to square root of 49, which is equal to 7. And important to remember the units here, it's in centimeters. So our final answer is that this length is 7 centimeters. So we've used Pythagoras' theorem to find out what the distance is from one corner of this box through to the other one, just using the lengths on the outside. So you can test yourself now by checking another through distance inside the cuboid. So if I open up the same cuboid, so same lengths, 3, 6 and 2 centimeters, and I flip it around, then I could construct another line from one corner to the other. I'll show that by putting in another right angle triangle. If you think about it, so we've now got it sitting flat, like you would normally see a shoebox, for example, instead of being upright like it was before. So no longer from the red to the red corner, but for this opposite corner to this opposite corner here. And so from that, you can see that its height of this right angle triangle is now the 2 centimeters, but we don't know either of the other 2 lengths. And so you would, for a little hint to help you out, construct the same idea by putting the flat side right angle triangle, which you know 2 sides off because in this case it's now the 3 centimeters for the height of this green triangle and 6 centimeters for the length of it. And so you can use Pythagoras' theorem to find out this shared length for both the green and the yellow right angle triangles here. And then you can use Pythagoras' theorem again to find out what this diagonal length is through the center of this box. So you can do that one as a little test for yourself.